should
Okay.
be here and can't be here for some reason. And if it's on your computer, then it's more complicated.
Okay, it's recording to the cloud, wherever that may be. So Brian, you again have the floor.
Great. All right. Well, as I said, thanks, Mike, for the great introduction. Yeah, and thanks for everyone being here today. So I'm going to tell you about a bit of my research, but not all of it. So this is part of the onion. I thought about giving a talk that went into a little bit of all of the things that I do, but I rather wanted to give perhaps a little bit more of the scientific and in-depth view. So we'll see how it goes. So the title, Control and Measurement of Quantum Optical Pulses, and hopefully by the end of the talk, you'll understand these images here at the bottom. Can you see my cursor, Mike?
Yes, I can.
Okay, thanks. Why are we not advancing? There we go. Okay, so here's a quick outline. I'm going to talk about, in general, what a quantum experiment is and give some motivation for the work that I do. And the message there is preparation, manipulation, and measurement of quantum systems. Then we're going to talk about optical pulses. So most of the work that I've been looking at these days is focused on short pulses of light and looking at their applications. Then I'll explain how we shape pulses and the trade-offs or disadvantages of classical pulse shaping versus this new area of quantum pulse shaping. And then talk about how we can use that ability to manipulate classical pulses to measure 1 and 2 photon states of light. And then I'll wrap up with just a few areas of future directions. All right, why are we there? So motivation. This was a great birthday present for me yesterday. So yesterday I turned, well, a number. On the 7th of October, happens to also, I also share a birthday with Niels Bohr. But motivation, being able to control systems, physical, or in this case, biological, is essential to progress in science, right? And so these two scientists put forth a way, something called CRISPR, to manipulate individual DNA strands and actually chop out bits of it. And I remember about 5 or 6 years ago, when I first moved back, actually it was about 5 years ago when I first moved back here, my college roommate is a professor at Berkeley and works directly with Jennifer Doudna. And he was telling me about this CRISPR thing. And it was like, wow, that's amazing. And here we are just a few years later, and these two scientists get the Nobel Prize. It was really amazing to see, and how excited my old roommate was about all of this. So motivation, being able to control systems, advances science. So let's funnel things down. I had a little blurb in there about quantum physicists, biology doesn't really work well, at least not at the moment. So we're gonna isolate single quantum systems, and within this idea of a quantum experiment, we have 3 key elements: sources, circuits, and measurements. So in a source, we prepare a quantum state, some kind of quantum system, maybe a single photon, a single electron, depends upon what your experimental area of expertise are. You prepare that, it's represented mathematically by some kind of wave function, for example. Then you let the state evolve, either naturally under some Hamiltonian evolution, or you might drive the system some way to do something. And so that's our state evolution, and you can represent that by this chi, which is a tensor that maps input states to output states. And lastly, you make some measurements, right? As an experimentalist, you want to make some measurements to determine what happened. Perhaps you want to measure what the state, how the state's evolving, to maybe estimate what the Hamiltonian is. And so you need some kind of measurements. These are represented here by these, mathematically by these operators, these pi sub j's, where j labels the measurement outcome. And on the bottom, I've just represented polarization of individual photons, for example, and this is a polarizing beam splitter that separates horizontal and vertical polarization, going to these two blobs here that represent click detectors registering a photon or not. So this is the essence of what I'm going to be talking about. Is, you know, we have light sources. You could think of that as a laser pointer. Well, that's a useful tool. Light bulbs, perhaps less useful for quantum experiments. And then, ideally, what we'd love to have is a push button single photon source that spits out one photon and only one photon at a time. And so, we work on all of these objects in our labs and try to basically make them all better. So why would you?
Sorry, Brian, before
Yeah.
you go to that slide on the previous one, so I get what the left thing is and I get what the right thing is. And I know what you mean by state evolution, but what's that sphere got to do with it?
So the sphere is what we call the Bloch sphere or the Poincare sphere. It's a three-dimensional representation of polarization. So any polarization vector can be represented as a point on the sphere's surface. And so diagonal, the D here is the diagonal, the A is anti-diagonal polarization. So you would have those two. Horizontal is in the front here in red, vertical is at the back, and then right and left circular polarizations are at the north and south poles. And then elliptical polarizations will lie somewhere on the rest of the sphere.
Okay, thank you.
So it's a way to mathematically represent, instead of having, it's a complex vector essentially on a three-dimensional surface.
Okay, thanks.
Yep. There. So back to the motivation. So what can we do? If we can make our experiments better, we can make better measurements. Better measurements allow us to test our fundamental theories of physics. And in quantum optics, these are a list of experiments that you require us to quantize the optical field or the electromagnetic field. So we have the Casimir force between parallel plates, the Lamb shift in hydrogen, spontaneous emission as described by Weisskopf and Wigner, photon antibunching. So the fact that only if you have one emitter, one atom will only emit one photon at a time. And then quantum noise in squeezed light. So being able to cut down the fundamental vacuum noise in a particular, what we call quadrature of the optical field, and violations of Bell inequalities. So all of these have benefited from improved techniques, experimental techniques to probe these foundational physics problems. And also, as I said, we can use those to do something different as well. So we have applications, and this is a big area of a big push and in quantum these days is quantum technologies or quantum information science, where we're applying the rules of quantum mechanics to information processing like tasks. From computing here at the top, linear optical quantum computing is LOQC. That little circuit on the right-hand side represents waveguides, and where the paths cross, that's interference or a beam splitter. You have quantum communication, so Alice and Brian having a conversation. You can have secure exchange of information by utilizing individual quantum systems. You can simulate other quantum systems if you can control, say you have control over one system very well, you could simulate perhaps another. Quantum enhanced sensing, so I give two examples here on the bottom. LIGO is now going to be using, correct me if I'm wrong, our LIGO collaborators here, but squeeze lights injected into them to reduce the noise levels. And so this is a huge application of quantum light in sensing and quantum networking as well. So being able to distribute entanglement between long distances could perhaps lead to enhancement in telescope sensing. So large baseline telescopes where you have two different base stations. And by sharing coherent entanglement across those two base stations, you can potentially gain a quantum advantage in the sensitivity. So that's the motivation. So what do we want to do? Make improvements in each of these little boxes. And that's what we do in our lab. So let's now take a step further down and talk about what is a pulse. What is an optical pulse? Well, optics refers to a specific region of the electromagnetic spectrum, right? And the reason why we choose this region of the electromagnetic spectrum is that if you have low frequencies at room temperature, there's lots of ambient noise photons that populate those frequency modes, and at higher energies or higher frequencies, you run into an issue of generating eventually generating electron-positron pairs, which that becomes then matter is no longer conserved. And so we're in this regime where we don't have to worry about the vacuum or the ambient room noise populating our photon modes. And we're not such high energy that we have to worry about other high energy like issues. So in this regime, in any of these regimes, first thing you do is you solve Maxwell's equations for whatever geometry. And usually we want to make a beam-like approximation. This is the paraxial approximation. So we have a beam traveling in a particular direction. And then we want to look at a certain spectral region. So that gives us a carrier wave here on the right. And this beam is described by this U function, some mode function that describes the transverse shape and it will change as you propagate along the direction of propagation. And then you have this alpha term. This is what I would call the slowly varying envelope. Alpha doesn't vary on a time scale compared to the period of the optical cycle. So it's slow compared to the period of the optical cycle, and it gives a slow modulation about that. And it's this alpha that describes our pulse structure of the light. So the linearity of Maxwell's equations.
Excuse me, Brian,
Yeah.
Question?
Yeah.
So could we go back to the previous slide? So you said that alpha is very slowly varying. What about U? Is that also assumed to be slowly varying?
Along the propagation axis as well. Yes, so that's the paraxial approximation. It's also limited.
So both U and alpha are slowly varying?
Yes.
Okay.
But with respect to different, U
right.
is slowly
varying. U is slowly varying with respect to time, and alpha is slowly varying with respect to time, and U is slowly varying with respect to space, with respect to K0.
Yeah, and K0, yeah.
Great, thank you.
Yep. So the linearity in these approximations, then we can write any electric field amplitude E of x and t as a linear superposition of these things. The Maxwell's equations are linear. That implies we can have linear superpositions. That means we can have wave packets. And it's these wave packets that we're interested in here. So pick a direction of propagation. You have a polarization vector, these EL or ER or superpositions thereof. You have transverse modes here. These are transverse electromagnetic modes. And then you have this longitudinal degree of freedom. And it's that longitudinal degree of freedom that we're going to focus on for the rest of the talk. We'll suppose that the light then occupies a specific direction of propagation that we know, a given polarization and a given transverse profile. And so we're only going to be focusing on this temporal envelope, right, as given here. So once we have a pulse of light, what can we do with it? So we've been able to now get down to 10 to the minus 15 to 10 to the minus 18 seconds. These are pulses with duration of that sort of temporal duration. So this is the femto to attosecond regime. And being able to get a pulse of light that short allows you to make measurements on those sorts of timescales. This was the Nobel Prize in 1999 for making essentially time-lapse photos. Think of it as molecular motion. So this is sort of the timescale. Femtoseconds are the timescale of molecular motion. And attoseconds are only recently being generated, hundreds of attoseconds currently. And the ability to generate these attoseconds, the timescale of electronic motion within atoms is on that sort of attosecond timescale. And so it allows you to probe the dynamics of these systems at ever shorter timescales, and allows you to get more insight into what's actually going on in these things. In addition,
Brian?
Yes.
Sorry, Brian. No question. maybe I've done this arithmetic wrong, but it seems to me that a femtosecond pulse, the longest pulses you're talking about here, would have a duration, have a length at the speed of light of about 3 times 10 to the minus 7 meters, or about 3,000 angstroms. That's about the wavelength of visible light. Have I done something wrong there?
No, you're exactly right. So, when you get down to about 10 femtoseconds, you're getting what we call the near single cycle regime.
Mm-hmm. So the approximation you talked about in the previous slide of assuming that the envelope is slowly varying is going to start to break down.
Yes, so that's absolutely correct, John. And there you have to be very careful. You run into a regime where you have this carrier envelope phase offset. So normally you don't care about the relative phase between the carrier frequency and the envelope function, but then it becomes extremely important at these near single cycle regimes. And yes, you can't say that your solutions to Maxwell, you can't use those as solutions any longer, but you still gain insight, and there's just more things you have to take into account. So yes, you're right. Once you get down to that regime, and attoseconds, their carrier frequencies aren't in the optical. They're getting close to X-ray regime or soft X-rays. Yeah.
Mm-hmm. Okay,
yep.
Great, thank you.
Right, so you can probe dynamics of very short time scales. In addition, the Nobel Prize in 2014 was given for something called STED microscopy, where you can basically use nonlinear responses of fluorescent materials. You can bleach them out and then gain effectively higher resolution when you make an image in your microscope. You also can see here on the bottom of the slide here where you go from nanosecond to femtosecond pulses in etching away material. So you can machine away things much more smoothly with very short pulses of light rather than these longer pulses where you run into heating effects that cause rough surfaces. In addition, there are other motivations for ultra short pulses, or what we'll call ultra short pulses. These are the femtosecond regime. So I mentioned this inscription or waveguide writing. Telecommunications, obviously, we use short pulses every time we make a phone call these days. That it's anything that goes into optical fiber is based upon then not necessarily femtosecond, but short pulses of light, and the ability to manipulate those is important for telecommunications. Metrology, so this LiDAR, it's light radar essentially, is used to map out with finer precision than radar. So you can measure here forests, for example, by looking at time of flights. You bounce off a pulse and look at the reflection timing. And then distributed sensing in optical fibers and planes or other things is also important for this. So what about quantum pulses of light? All right, so why bother with pulses for this? So it gives us a larger information capacity to encode information in a pulse or many different types of pulses. The shape of the pulse is essentially the symbol that you'll use to represent some letter of the alphabet. And so you have higher dimensionality, which allows you to get more information per photon that you're sending along your network, for example. So again, take a hint from classical telecom where they do wavelength or time division multiplexing. We can also then use quantum light to do studies of dynamics and perhaps studying things like energy transport or molecular dynamics. This is something that has been ongoing with myself, Michael Raymer, Andy Marcus, wondering whether or not we can use entangled light to probe molecular systems. And that's a whole other talk. So, and yeah, hopefully we'll get to tell you about that another time. And then being able to just manipulate the pulse mode shapes so that you can connect up two disparate types of quantum systems. So for example, two big names in quantum computing right now are, or platforms rather, are superconducting qubits and trapped ions. And they talk to the electromagnetic field at very different regimes. So superconducting qubits act in this sort of microwave regime, and ions, they interact with the electromagnetic field in this sort of visible regime. And so to translate those two, or to get those two to talk to one another, you have to bridge these huge orders of magnitude and energy. And so being able to manipulate the spectral temporal mode structure of the light is important to get these two to link up. So what is the quantum state of the electromagnetic field? Well, think of photons and modes. So each mode of the electromagnetic field acts like a silo into which you can put excitations or photons, or you can have superpositions of these. And so when you look at the literature and you learn quantum optics for the first time, you find that we tend to work at two different extremes, either one mode and many photons put into that mode, or one photon, one excitation across many modes. And so we have our one mode, and the quantum state will be represented by the number distribution and the coherences between each photon number in that mode. And there are different representations we use for this. So you can think of this plot on the bottom. N is the number of photons, and this is the probability of having photons, certain photon numbers in a particular, in this particular mode that we've chosen. Or you have these, what we call quadratures, Q and P, and they oscillate, they rotate this state here. The reason why I've drawn it out. So if Q and P are 0, that means vacuum. Just think of this as the real and imaginary part of a complex electric field amplitude E. And so this thing will rotate around at the optical frequency, but we go into what we call the rotating frame, which means it's stationary. And so this normally an electric field you would think of as a phasor. And so it's a single point in this phase space, but because vacuum fluctuations, it blurs things out. And that's why I've drawn this as an orange. As you get closer to the origin, that becomes more important. If you have a very strong electric field amplitude that's far out from here, that vacuum noise is minuscule compared to the overall amplitude, and it looks like a phasor. But as you get closer and closer to the origin, this becomes very important. Okay, so there's that. And then we have our fixed photon number. So one excitation in the electromagnetic field, but now you need to know what modes does this thing occupy, or superposition of modes. And so it's the mode structure that becomes important. So Debbie Downer, for those who are of a certain vintage, comes in and says, well, modes are classical, right? They're a solution to Maxwell's equation. So what's quantum about it? Well, being able to manipulate and generate individual photons in well-defined modes is the quantumness, and doing that without destroying this single excitation or perhaps superposition of two photons, that's the quantumness. And we'll come back to this in a bit. So my research spans both of these regimes, and I work with both single mode multi-photon or single photon multi-mode regimes. And I'm going to focus on the single photon or two photon states across many modes. And the modes are going to be these temporal modes that I've introduced, these pulsed modes of light. So what is the state of a single photon? Or in other words, how do I explain? So what I've just explained is that if I know I have a single photon, a single excitation of the field, then it's the state of the photon is the mode function that it occupies. So you might think of that as the wave function of the photon. And you can get into arguments about, well, what does that mean? But it turns out an electron, its wave function is really just a mode that's a solution to the Dirac equation, if you want to go relativistic, or the Schrodinger equation for non-relativistic regimes. And so it's just a solution to this wave equation, or this field equation. And when I populate that with a single excitation, then you can call that a wave function. All right. So the single photon state is its mode function. And so I can write the electric field, the state of the electric field for a single photon here in a particular mode psi. We're going to choose this to be the frequency mode basis. Is just this creation operator acting on the vacuum. The creation operator here can be written in terms of monochromatic creation operators weighted by this wave function psi, or this mode function. So this mode function, again, is a solution to the Maxwell equations. And it has the following interpretation. Psi can be interpreted as a probability for detecting a single photon, or the probability amplitude for detecting a single photon near a frequency omega. And it has some width, delta omega. And you can think of this as essentially the spectrum of the individual photon itself, or a collection of them as you measure this. So it's important to remember, though, that the mode function has both amplitude and phase, and it's that phase that's usually very difficult to extract or measure, and we'll be talking about that shortly. And you can encode information in the shape of these pulses. So here on the right is a secret message encoded in what we call the Hermite Gaussian basis. So you can expand any pulse mode in a moving frame in terms of, say, the Hermite Gaussian mode shapes. So these modes also have a representation in the time domain, right? And they're related through a Fourier transform. So that's just to keep you remembering. So psi here of omega is an amplitude times a phase factor. And you Fourier transform that, you're going to get some temporal envelope and some temporal phase. And it's important to note that these phases are not Fourier conjugates of one another. There's no simple relationship in general between the phis. Okay, here is where I got to get the music queued up. So another way to look at a pulse is through what we call a sonogram, or a chronocyclic representation. And so we're familiar with sonograms in terms of music. So we've got Moonlight Sonata is one example that I've used in the past. So of something called an arpeggio, right? So if I can remember, dun, 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 where each note is played one at a time. And you can see each note here on the left, 1, 2, 3, it's progressively getting up. Time is along the horizontal axis, frequency is along the vertical axis. And so this week, as some of you may know, Eddie Van Halen passed away just the other day and was very influential in using arpeggios on electric guitar. So what does that sound? So keep that in mind. That's the sound of individual notes as you rise up as a function of time. We can do the same thing with pulses of light or the pulse mode structure. And so this is what we call a Wigner representation, or a quasi-probability distribution. And you can use that to represent pulses. So here on the left, we've got two individual pulses. And so frequency is again along the vertical and time is along the horizontal. So we've got two pulses, this these two yellow blobs. How does that come out on screens? Is that okay? All right. So, and in the middle, you've got this sort of fringy pattern. And that fringy pattern represents coherences between the two pulses. The fact that they're not a random mixture, or the phase between them is actually fixed. And if you look in the frequency domain, oops, why are we going forward? If you look in the frequency domain, you will see those fringes. And in the time domain, you'll just see these two pulses in time. We can also shift the relative frequencies, and you end up with this plot here where you've got two blobs. And if you look at the frequency or the time distribution, time of arrival, you will just see two blobs in time or two blobs in frequency with no interference. But in the joint distribution, this Wigner representation, you do see signs of the coherence between those two in these fringes. Okay, and so this is essentially this is a score for photons, or the spectral and temporal properties of light. And we're going to use those to represent our pulses later here as we go through. So now I want to turn to, that's talking about sources, and just, I won't explain what we do in the lab. I'll just leave that for now. I want to focus on how we manipulate these pulses and how we detect them. So yeah, how do you go from this sort of Gaussian shape to a double pulse, or let alone some complex Hermite Gaussian pulse. So this is the intensity profile of one of these Hermite Gaussian pulses. So how do you go from the left to the right? How do you manipulate those things? So classically, what people do is they amplitude or frequency modulate. And so they can chop amplitude, or they can add amplitude, gain. And this is, you can chop things by putting a shutter in, or you can squeeze things through a filter, a spectral filter. And here's an example of a spectral filter where you've got what is called a pulse shaper. So you've got a grating here. You've got your input pulse comes in. You've got a grating, G1. It maps frequency onto angle. Then the lens, L1, maps angle of the outcoming light onto position in the focal plane of that lens. And so if I put an amplitude or a phase mask here, I can chop out different frequencies as a function of position, or I can put a gain medium there to add more gain to, or add additional amplitude at those positions. And then I can recombine it on through L2 and G2 and get a different pulse on the output. But the problem is that that is incompatible with quantum light. So if I have a single photon and I put it through an amplifier, I'm going to add photons, and that adds noise. I know, well, there's this thing called the no cloning theorem in quantum, where you can't actually clone a quantum system. You can't reproduce it exactly without adding this extra noise. And so that's a problem. And by filtering, you're cutting out. So if I try to chop out some of the amplitude, I'm losing my photon. And so you won't get it back. So you have to do something different. And so all you can do to address these temporal modes is by phase applications only. So here we've got a temporal amplitude, psi of t, and we're going to add a linear phase that goes as big omega times t, right, across that. So think of it as a pulse in time, it's moving along, and I'm going to modulate somehow a linear temporal phase ramp. What does that do? Well, in the Fourier domain, right, psi of t is going to transform from its input original thing to this multiplicative phase factor, which means in the Fourier domain, I've shifted the frequency of that pulse, the central carrier frequency. And if I do that in the frequency domain, I add a linearly varying phase across the spectrum. I'll basically add a shift in time. It's a time delay. So time delays, for those who aren't familiar, are really easy to do in the lab with a laser. You just bounce it off a couple of extra mirrors, making the path length a bit longer. However, to get a spectral shear is not so simple. And we've done that. So how? Well, we use something called an electro-optic phase modulator. So this is driven here by a sinusoidal voltage source. It's very rapid in the radio frequency or to near microwave regime. And this EOM, it changes its phase with the voltage that you apply to it. So it implies a phase, or applies a phase to the optical field here, E of t, in red coming through, that's proportional to the voltage. And depending upon my pulse, if my pulse is very short compared to the duration of my RF field, then I can lock that phase modulation to the pulse coming in, and I can have a linear phase across that pulse. I can have it positive or negative, which means I'll shift up or down in frequency. And I can also sit on this quadratic part. And that quadratic part is like a lens in time, right? So a lens adds quadratic varying phase in space. So the lens, it has a sort of quadratic shape, parabolic shape. And that adds this quadratic spatial phase. In time, here we're doing the same thing. And so we've experimentally shown this quite a few years ago now, and it's become a useful tool in our lab to shift single photons around. And so this paper here, and this technique was then recently used to actually do multiplexing as well from heralded single photon sources. And I'll just point to that here. So quadratic spectral phase followed by quadratic temporal phase will compress the bandwidth, well, or it can expand it depending upon the sign of the quadratic spectral, or rather temporal phase. So let's look here and think about, here's our pulse and frequency. So this is the spectral property of the pulse. This is the spectrum of the light. And each component is seeing a slightly different slope of a linear phase in frequency. So if we remember, a linear phase in frequency gives me a time delay. So each color here is going to have a slightly different time delay. And that leads to what we call chirp. Right? So meaning a different color arrives at a different time. And so we put our input pulse here. It undergoes this quadratic spectral phase. And what we get on the output is here on the right. It's got now correlations between the color and the time of arrival. And so think of it in the sonogram picture as, or, right? So either you're going up or you're going down in frequency as time goes on. And so this stretches the pulse in time, but it keeps the spectral content. Now, if we apply to this pulse a quadratic time varying phase, remember the time varying phase, think of this in this linear regime. So each component in time sees a slightly different time, slightly different linear time phase. That linear time phase corresponds to a frequency shift. And so each component along here will see a slightly different frequency shift. Some will be positive, some will be negative, depending upon where along this quadratic you lie. And what you can do is, if you have it flipped, you can compress the bandwidth or expand the bandwidth, depending upon the sign of the quadratic here. And so you can, in this case, we've compressed this bandwidth to be narrower. And this, we've done this experimentally and around the same time. So this is work from my group in Oxford. So here we've done this experimentally. We've got this single mode fiber, which does this chirping out. That adds this quadratic spectral phase. And then we have our electro-optic modulator here that applies the time varying quadratic phase. And we have these three different plots of input is in orange. And then we have either the green or the blue, depending upon the sign of the quadratic we apply. We can compress or expand our bandwidth. And we've gone on now to make significant improvements in this with lower losses and other things. But that was the first demonstration of this manipulation. So currently what we're working on here, and one of my students, James Ashby, has been working on is arbitrary manipulation. So this picture and this image in the middle is what we would call standard spatial mode unitary. So these are these waveguides, and you put a photon here. In this waveguide, it'll bounce around in these interferometers, and these little gold or orange bits are phase shifters. So you need nested interferometers, and wherever these paths cross, that's a beam splitter, right, where you can have interference. And so if you put in photons here along the input level, they'll bounce around and interfere with one another, and you'll end up with a particular pattern of where photons emerge at the output. And this is used in a lot of quantum information applications, linear optics, quantum computing, something called boson sampling, something called a quantum random walk, using photons as your walker, and photon star of communications. So in the low light limits of trying to do some sensing, you can, or communications protocols, using the ability to manipulate this mode structure is important for these things. And in particular, we want to map this sort of picture of this interferometer network onto the temporal modes. And it turns out we've discovered that in order to do that, you have time varying and frequency varying phase pairs. And if you want to map essentially n input modes to n output modes, you need roughly n-ish pairs of time varying and frequency varying phases. And so you can read more about that. We've recently posted this on the archive a couple of weeks ago now, and James is building experiments to work on this. So the last bit I'd like to talk about is detection. So in order to measure the spectrum of single photons, this is now quite a few years ago, you map frequency onto position using a monochromator here on the left, and you scan the fiber tip, or if you're really lucky, you might have an array of single photon detectors. That's not usual, though, in a lab. So what we've developed over the last few years was mapping the frequency onto time, and then using a fast time tagger. So here we've got a pulse coming in from the left, moving to the right. It goes around this object called the circulator. And this is a device that works off of the non-reciprocity of the Kerr effect. So a rotation in with a magnetic material with a Faraday constant, and it gives a rotation of the polarization as you propagate through, and it's non-reciprocal. You can't go back through it. And so this one-way device, if you come in from the left, it comes out on the right. If you come in from the right, it goes up to the top, and et cetera, and you go around and around. And so we come in on the left, we go through a chirped fiber Bragg grating. So this is essentially a big mirror that reflects different colors at different positions along the fiber, and it's made out of an optical fiber. So red comes out before blue is the upchuck of that. And then we have a fast avalanche photodiode and a time to digital converter TDC that time tags all the input light. So when did a photon get detected? And so that when did a photon get detected is mapped onto the frequency through this chirp fiber Bragg grating, and we can measure all channels of the spectrum simultaneously. And so it allows us to get on the order of 1,000 modes in a single shot, which significantly increases our ability to make measurements instead of having to scan 1,000 bins and wait at each one while throwing away most of the light, which you would do on this scanning monochromator. So that's enabled us to do a lot of new things. So this was published a few years ago as well. We can measure pairs of photons. That's on the top here, where they've got the joint correlations of the two photons. So what colors, and we'll get to this in a moment, what this means on the top. Or if we have two pulses, you should see these spectral fringes again, and we were able to do that with single photons, and in a matter of minutes, rather than usually these scans take hours or overnight. So how do we can measure the spectrum? How do we get the phase for our single photon? Well, we turn to classical techniques, something called spectral interferometry, or SPIDER, spectral shearing interferometry for a direct electric field reconstruction. So we have our pulse, psi, that's described by some mode function psi of omega. It's a single photon, and we're going to split it into this Mach-Zehnder interferometer. On the top, we're going to give a time delay, a temporal shear, and that takes our mode function to the following, multiplied by this exponential phase factor here, e to the I omega tau. And we're going to use our spectral shear that we've implemented and shift the spectrum of the bottom arm by an amount big omega. And so the spectrum on the bottom is shifted a bit, and the amount of shift is not going to be such that it completely is orthogonal to the upper path here. So basically, we're not going to shift by more than the bandwidth of the optical pulse itself. And so what you get on the output is a spectral interference pattern. And that spectral interference pattern, right, we're measuring as a function of omega for a fixed big omega and tau. So we get the shifted spectrum squared plus the unshifted spectrum squared, and twice the real part of the cross terms. And those cross terms, that contains information about the spectral phase, right? So this cross term has the phase at omega plus big omega minus the phase at omega. And we also have this offset omega tau. So we can extract this spectral phase in the following way. So we take our measured spectrum, we Fourier transform it, and we can then filter the sideband at that time delay tau. So we need to pick our tau appropriately, and inverse Fourier transform back. Here's the real and imaginary parts of that filtered spectrum. And we can extract from that the argument. And that argument will have this phase difference. And that phase difference is essentially the derivative. If big omega is small, it's proportional to the derivative of the phase as a function of frequency, and we can numerically integrate that. So that's how we extract then the spectral phase of our single pulses. And we've done this now with the following type of pulse. So we take a single photon and we apply a linear phase on half that goes down and a linear phase on the other half of the spectrum that goes up. And in the time domain, that, right, so each of these linear spectral phases corresponds to either a time delay or advance with respect to the central time of the pulse. So we'd expect to have a pulse that goes half this, that has some color that's ahead of the other color. And so we'll have two pulses that are separated. And we can have a V phase or a lambda phase. And that's what we reconstruct. So these are the experimental reconstructions. So we can now readily reconstruct the pulse modes of individual photons with this technique. So then after that, we've turned now to using these tools of spectral shearing interferometry to reconstruct the state of pairs of photons, where you might have correlations or entanglement. And the source of our two photons is something called spontaneous parametric down conversion, SPDC. And in this case, this is a nonlinear interaction between a strong optical field here in blue called the pump and a second order nonlinear material that couples to these signal and idler fields. These are two different fields, or actually three different fields. The pump is blue. Usually it's about 400 nanometers, and the signal and idler are going to be in the red. And the sum of the signal and idler frequencies has to equal that of the pump. And so what you can show is that on the output of this down conversion process, this SPDC process, you get a pair of photons sometimes. One of these pump photons spontaneously splits into this signal and idler pair. And they're described by this joint spectral amplitude F of omega S, omega I. And that's what we want to measure. And this is the quantum object now that we want to look at. It's the probability amplitude of creating a pair of photons with these two frequencies. And they can have, we can make measurements of the joint spectral intensity by sending the signal and idler to two spectrometers and looking at coincidence events. And so here on the left, we have pairs that are correlated. That means they're entangled. Well, at least they have correlated frequencies. Not necessarily, we'd have to look in the time domain to see true correlation or true coherence between them. And on the right, we see there's no correlations in the frequency, or very little correlation in frequencies. And so the the pair source on the left is what we would call entangled, and we can rewrite that joint amplitude in this sum called the Schmidt decomposition, or the factorable states on the right, which can be written as a product state of two functions multiplied together, one for the signal and one for the idler. So in order to measure or characterize a pair source, a photon pair source, we need to measure both the amplitude and the joint phase of this thing. So the joint spectral intensity is easy. As I said, you send the signal and idler photons to two of these time of flight spectrometers and you measure it. And we can do that easily now in our lab. But it contains no phase information. So how do you access that phase? Well, we're going to use our electro-optic shearing interferometer, this spectral shearing interferometer. So we'll send one of our photons, so 1 and 2, those could be signal and idler, or we can flip them. One will go to the spectral shearing interferometer, and that's coupled to our time of flight spectrometer, or an individual time of flight spectrometer, and make measurements. And so what we'll see are fringes in that joint spectrum that we measure. We can Fourier transform that again. It now becomes a two-dimensional beast. We filter that out and we get fringes. This is sort of the inverse Fourier transform back to the frequency space, right? And what we've done is looked at two different cases. One where the pump photon, the blue photon, has no chirp. So it's Fourier transform limited. It's the shortest it can be. And there we see essentially no correlations in the phase. But if we chirp out the pump, that means the blue photon that's pumping this nonlinear process, generating these pairs of photons, it will have the redder components arriving before the bluer components in the material. And so time and frequency are coupled between those two, and that gets imprinted onto this signal and idler pair of photons on the output. And that becomes, in the spectral domain, it's represented by spectral phase that's correlated. And you can see that these fringes in the inverse Fourier or the reverse Fourier transform, the filtered Fourier transform, are slightly tilted. And so from that, we can extract out then what this correlation phase is. And again, it's related to the color of one photon is related to the time of arrival of its twin sibling. And that's the correlation that you're measuring. So if you measured time and frequency, time of arrival and frequency of the other photon, you would see a correlation in this. But we're only measuring the spectral properties. And from that, we can extract all of that time frequency correlation. So here we have another representation of that. On the top, you've got the unchirped pump, and you see that the amplitudes are given by the dotted or the dashed contours, and the phase is the solid contours. And the amplitude is essentially near zero for the top, and you have significant phase structure here on the bottom where you've got the chirped pump. And this just came out about a week ago, or less than a week ago. So yeah, we're only on the 8th. Right, so let's wrap it up. Quantum experiments, think of sources, circuits, and detectors. And anything that we can do to improve these things will impact both fundamental and applied science. I'm focused on pulsed modes and talk mostly about those. They're good for spelling, information encoding, how we can manipulate those things, how we can measure those things, and beyond. So I'd like to thank those who made it possible. Here's our team here in Oregon now, the Optical Quantum Technologies Group, and some friends who've helped along the way. So I'd like to thank everyone as well here today for your attention.
Thank you, Brian. I'll clap for everybody since most of you are muted. Okay, everybody. So I'm browsing through the question, well, the chat window. There's a lot of comments here about DeLorean sports cars and tattoos and other things like that. But there is one question here. It says, why are they called the signal and the idler?
Oh boy, that's historic. That's a so yeah. The way that this spontaneous parametric down conversion process, and Mike, you probably correct me if I'm wrong, but if I remember correctly, historically you had this signal photon, or you didn't use these things to generate single photon pairs, you used it as an amplifier. And so if you seed this process with a red signal beam and you want to amplify that signal, you want more signal, then you have this idler that sits to the side and you generate that too in the same time, but you just throw it away. And I think that's essentially the origin of the names for those two modes.
Yeah, that's within nonlinear optics, but it probably goes back even further to electronics.
RF, yeah, it could be RF as well.
Electronic oscillators. Maybe somebody here knows about that old radio technology. It might even go back to mechanical oscillators. I'm not sure.
Yeah.
Let's see, I have a question I could follow up. Early on, you said something about having quantum light can increase something like the capacity of information in a network. And we know that there's the classical Shannon, coding theorem for noisy channels, and that the current optical systems are working pretty close to that limit. So in what way can, quantum states of light exceed that classical Shannon limit, and by how much is this feasible?
Okay, so I don't believe I said that quantum could enhance the capacity, but
you didn't, but you talked about information per photon. So
right, I did say information per photon, and the ability to use the temporal modes increases the information each photon can carry. beyond other encodings. So other encodings being, say, polarization that's usually used. Now, you actually can increase the capacity using something called superadditivity, which uses entanglement in a channel. And yeah, that's about all I know. I'm not going to go, I'm not prepared to answer too many questions about that. But I do know there's work that has shown if you can share entanglement through a channel, you get what's called superadditivity, so that the information content is actually more than you would, more than the sum of the parts.
Mm-hmm. Yeah, here's a question from Hailan Wang. How can you entangle two temporal modes?
So I guess, yeah, you need a beam splitter, right? And so the simple way to think about entangled modes, I would say, is think of a single photon going to two paths into a beam splitter, and then you have this superposition at the output. So the modes have a superposition of the photon excitation being in either arm, and you would say that those modes are now entangled. And so you'd need a temporal mode beam splitter, which is what James is essentially working on. This multi-mode unitary transformation.
Mm-hmm. One question from Dean Lively Brooks. I'm not quite sure I understand it, but he says, if the blue photon entering the PDC is chirped, does the down sampling material, perhaps means down conversion material, determine the degree of entanglement of the red output photons?
So good question. Let's see if I can go back, not easily. So the entanglement, the degree of entanglement is primarily, in this case, set not by the material properties. Let me see if I've got. So the material properties have been chosen so that the joint amplitude has no correlations. So if you just looked at the spectral intensity, there's no correlations. The only way you can introduce correlations are through the pump pulse. But if you choose different materials for your interaction, then yes, the material can introduce entanglements there as well. And that's through something called phase matching in nonlinear optics speak for the experts.
Okay, we have time for maybe two more questions. One says, it seems as if things work like they should. That is, as theory predicts. Obviously, it takes a lot to successfully demonstrate this in a lab. Is it true that things work as they should, or are there things you found that are surprising?
So I'm telling you the nice story after we've packaged everything. Of course, there were challenges, tons of challenges. A lot of it's technical and probably boring for most people. We learned a lot about radio frequency technology, and we pushed the envelope on that. We're also getting to the point where some of the stuff that we want to do, there just isn't technology available, or it's research grade. And yeah, this is a direction that we're pushing. I guess, yeah, to answer the question, no, we haven't really run into anything that our predictions haven't made yet. But the point is that we would like to keep pushing so that we eventually get to that regime.
Mm-hmm. Okay, one final nice question. What is your, sorry. There's more questions here. What is your favorite potential application that you'd really like to see realized?
Yeah, so with the pulsed modes, I'd say there are, well, there's probably two different applications. One is, and so just think about what you do with lights. You look at stuff and you communicate. Smoke signals are like the original telecommunications. And I think those would be really great applications of these technologies. And we have worked in the past on doing quantum key distribution, which is a protocol for communications using these pulsed modes. It's just challenging. And yeah, so I'd like to do that. And also sensing. So metrology, being able to measure. So pulses are good for measuring time of flight. And also we're looking at being able to select out particular temporal modes of light from, say, a stellar source. And by filtering that one, you block out essentially all other modes that have noise photons, and you can, by selecting out a single mode, you get better signal to noise ratio in your detection. And that's this telescope project that I mentioned briefly. So those are the two, and I guess within sensing, another one is this I did mention about using entangled lights to probe molecular systems or physical systems that have nonlinear responses. And that's another interesting area, I think, to work in. So those are the sort of three things that we're working on, and I'd like to see come to fruition.
Okay, one more question. It's related to the previous question, previous two questions ago. What is your favorite insight into fundamental physics that results from these experiments?
Mm-hmm. So one of the things that in dabbling around in these experiments is the speed limits to which information can be gained in a given measurement. So there's something called the quantum Fisher information, which tells you how much information about a parameter you're trying to estimate you can get from a given input light source. So if I have this particular pulse mode source and I want to know how far away something is, I know what mode I should put it in. And this Fisher information, I can optimize it for what photon number and what mode I should put my resources in. But then it doesn't tell me, quantum Fisher information doesn't tell me how fast I gain that information. And it turns out that you can actually, in some cases, determine that if there's noise, you might want to do different measurements. And so, yeah, Stephen and I still have to finish that paper. But the insight is that the choice of probes that you use, probe states, and the measurements that you make to probe some kind of dynamics, it depends on what thing you're trying to measure. And this gives you a recipe for figuring that out. And that's been interesting. And I guess, is that fundamental physics or fundamental metrology? I don't know, but I think asking what physics says about how much information you can extract is, to me, fundamental.
Okay, I think we should wrap it up. It's time to go to the pub now. So thank you very much, Brian, and I'll clap for everybody.
Andy Marcus had a question that I don't think was asked.
Yeah. I'm happy.
Well, yeah, but I'm the moderator and it's time to go to the pub. So I'm going to cut it off here and Andy can ask him that in private at the pub. So thank you very much, Brian, and everybody, see you next week.
Okay. Thank you, everyone.
Thank you, Brian.